case, because I'm down to draw everything out, but chemists are inherently lazy, so unless I know it's useful, then I'm not going to do it. This is probably not propaganda I should be spreading, I don't know. Well, okay, fine, and I guess I don't... Okay, the other thing you end up with is, of course, R, H, 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 with a plus. Because, you know, that acted like a base. It's up there because we don't care about it. We can see down to... See down to like here. So I think we're going to leave that here. Let me redraw this guy. Just to separate. Okay. So now we've got this guy, and we just made this. We've got a lone pair. We're going to use yours. Okay. So now this is nowhere near a leaving group, right? So if we've got some protonated ammonia and we've got a negatively charged oxygen, that only makes sense that it's going to be like, hey, you know what? You're unhappy, I'm unhappy. How about we just fix this for both of us? And we'll both be much happier. And everyone can go along with their day. So we do that. And then don't immediately redraw the thing we just got rid of. Okay. We make this guy, and we regenerate. And this is our aminal intermediate, aminal. It's an amine, but it's an intermediate. So, the line is a little generous, but it's fine. So, let's start with this guy. All right, so we've got this dude, and let me look at my bond association energies real quick. So I bet I can explain this too, but okay. Where are we? So what do we decide 350, or 732 minus 350 is?
382.
382. Okay. That's, I'm trying to indicate this is just the pi bond. I don't know. It's not something I've had to do before. Cn is 300. Hey. Aha. 615. So, well, I don't know. The pi part of Cn is 315? Yeah?
Yeah.
Yeah. Give me subtracting. Alright, so, I promise this is, hold on, where's my, okay, just for comparison, C single bonded to C is 348, and C double bonded to C is 611. So I'm not lying to you, I swear. When I say pi bonds are usually weaker than sigma bonds, it's just that with these electronegative lone pair having boys, they break the rules. So nitrogen also breaks the rule. It would rather form a double bond than a single bond, and our pi bond of this is not actually stronger than this, but like, it's okay. It really likes forming these double bonds. We're good. Rest of my colors. Okay. So, we have the ability to get rid of this, but it's not a leaving group yet, right? So, I think all of this can happen in neutral solution. I'm pretty sure. And I'm pretty sure the only reason that we need acid is to do the workup, because you can get, you can get to hemiacetal or an acetal, right? This is a stronger nucleophile, right? Am I sure it's stronger nucleophile? I want to say. So we can get here without acid catalyst, I'm pretty sure, especially since, no, yeah, everything we've done has not involved acid yet. So I think the reason we can break the rules is because we've got, it's just an acid workup. So, oh, why did I put that up there? That's a problem. Okay, so now we just go, hey, you know what? What if we do that? This, and O, H, plus. Now we made it into a good leaving group, so we can go like, really, they're gonna do that? Oh, okay, yeah, I would have drawn it like that, but okay. So now, we can, this guy is a good enough leaving group that it can piece out, and we could leave this so it turns into a carbocation, which will then resonate with the positive charge on both of those. But I'm just gonna do this because it's gonna be happier as a full octet anyway, so we're just gonna draw it the way that it is more representative. And now we've got this. A positive charge once again, and that. And so we can go, hey, you know what? I bet there's still draw it conveniently this way. Wait. There's still some amine floating around. So we can take some of that amine and deprotonate that, do that, and we get a lot of colors. And me drawing on my hands is what we get. And I drew this bent because lone pair, bond, bond, this guy's going to be trigonoplanar. Tropical. And that is our amine. Yeah? So, cool. We can do this. Nitrogens can be nucleophiles. We can make these imines. Ta-da. I'll push this back a little. Okay, so this is just sort of a, I don't know, they like to have things like this. Rhodopsin, it's called visual purple. There are a bunch of names like this. Like, there's one molecule that the common name of it is Blue Lake. Like, literally, that's like Blue Lake. And they're like, this is a noun. Blue Lake is a noun, and it is this specific molecule. And I'm like, oh, okay, like red dye number 2, I guess. So visual purple is one of them. Basically, it's also the amine formed in your retina with using vitamin A and a protein. So this is a thing that happens in your body, which is kind of cool. It happens in your eye. Biology. Look, organic chemistry is applicable to things. I don't know. Basically, it's useful for, what is it, transamination? Yeah. This isn't, I'm not gonna like quiz you on this, it's just, we should look up visual. I should put pictures of like visual purple and stuff so we can see how aggressively purple it is, because honestly, I'd like to know. Okay. Addition of nitrogen nucleophiles. We can do something else. So if we've got a secondary amine, we can treat it like a we can treat it like we did the primary amine, and we can do a nucleophilic attack, and then we don't have 2 hydrogens to get rid of, right? We only have 1 hydrogen to get rid of. So when we do that, it works the same way up to a point, and then we form something different. So oh, okay, yeah. So nitrogen nucleophiles, this guy, it forms an enamine. I was gonna do a whole mechanism for you here, but it seems that, I forgot, that's like all of chapter 19. So basically, it would be exactly the same. It's, we would try to form our double bond, but like we can't, but we still get rid of the water, so then we just end up making that double bond right there. And this is poorly placed because, okay, yeah, because we don't get to acidity of alpha hydrogens until here, but I guess that's part of why we're not, I don't know, honestly I would have skipped nitrogen nucleophiles, gone straight to alpha hydrogen acidity, and then hit this on my way out. But okay. It's a lot easier trying to follow the, like, rhythm of the book than it is to start trying to put things in your own order or like mix things between chapters. I tried doing that. It's not for the faint of heart or those teaching for the second time ever. So yeah, these guys are enamines. They're just single bond nitrogen with a double bond right next to it. So there's resonance all up in there, back and forth. We'll talk about that later, like for a whole chapter. Hydrazine-related compounds. H2NNH2, that's hydrazine. And aldehydes and ketones react with them to form hydrazones. So this, not a mechanism we need to know. This is just this plus this, some stuff happens, here we go, we get that, sweet. If we do that, let's see, derivatives of ammonia and hydrazine used for forming amines. Yes, we use some of these. I guess that's just for naming, but I don't care about the names, so. I've decided I'm not gonna ask you specific nomenclature questions on your exams. I am probably going to write them with the assumption that like basic nomenclature we've kind of got down, but I'm not gonna try to do anything to trick you. So like, I might not draw out a structure if it's already got it in there with the name and it's simple enough, but also I've decided I'm not testing you on nomenclature, so if during your exam you want me to draw something for you that only has a name, I'll do that. Yeah. Okay. Not during quizzes though, because I don't know, you can look that up. Where's my... Okay. Yep, amines and amino groups and carbonyls. This is the key mechanistic step in transamination reactions. So that's what we were trying to get to with what I thought the point of the other one was. But basically, transaminations are catalyzed by a specific group of enzymes, because enzymes are just like, oh, metal catalysts, you think that you're very clever. But instead they just make like a whole little pocket, and the pocket's really specific, and so they have all the like binding groups and electron density and like metals required to do all of the catalysis in their little pocket, but then they have a really specific pocket, so they do really specific chemistry, like only that specific chemistry. And they're like way faster at it. I don't know, because the pocket like holds it in the correct orientation so that they don't have to just bang into each other in different, like bounce off of each other in different orientations until finally it hits the right orientation. I don't know. But enzymes are really good at catalysis, and they catalyze like very specific things. But transamination is just, we had an amine and we switched it out with another amine. Wait, right? Yeah, a donor amino acid and a new amino acid, right? transamination. We're switching, okay, so we're switching those guys between each other. One of them gets to be a ketone, and one of them gets to be an amine. And they swap who is who. That's all transamination is. Okay, I'm not gonna test you on that. God, why would I wanna go over that? I don't wanna draw that. You don't wanna draw that. And like, you can't teach a mechanism just by pointing at the little pictures up here. I don't know why I didn't hide that slide. Okay, acidity of alpha hydrogens. Here we go. We talked about nucleophilic attacks where you do that in a basic environment and an acidic environment. One of them you protonate the, oh, well that's perfect timing. One of them you protonate the oxygen to make the carbonyl a better attackee, electrophile, and the other one you just straight attack and then you can protonate later. Now we're gonna move on to a whole new class of stuff, acidity of alpha hydrogens. So have a break and we'll come back and do some stuff, some chemistry stuff.